This video is sponsored by codingskill.net. Please visit our sponsor. Let's look at the quick select algorithm. This is based on Horace's partitioning scheme. It finds the kth smallest number in an unsorted list. Instance of the problem is defined through a numerical input list A, lower and upper indices defining a sublist, and a positive integer k. It searches for the kth smallest number in the specified sublist. What is the size of the problem? Size of the problem is the length of the sublist. What is the base case? The smallest instances of the problem in this case is lists that contain a single element, and lower and upper indices are identical. So another base case. If so, we return the element in the list. The list is arranged in three parts. First sublist contains the elements of A that are less than or equal to pivot. Then list with only one element containing the pivot, and third list contains the elements of A that are greater than the pivot. So in the input list, we first pick a pivot. This is the index of the pivot. It could be k minus 1. The function that implements Horace's partitioning scheme returns IP. We can check whether index of the pivot is equal to k minus 1. If it is, then the pivot will be the kth smallest element in A, and the method terminates at this base case. What is the recursive case? In the recursive case, we reduce the size of the problem by considering either the if the index of the pivot is greater than k minus 1, then the location of the searched element will be smaller than index of the pivot. Thus, we can focus on the sublist to the left of the pivot, as shown in this diagram. Let's consider the index of the pivot is less than k minus 1. We solve the subproblem related to the list to the right of the pivot, as shown in this diagram. This is the problem decomposition used by quick select. Let's look at the tail recursive function. The quick select method takes 4 parameters: the input list A, the lower and upper indices, and the kth element, which is an integer. If lower and upper are the same, we return the element at that index, and this is the base case, and we are done. Otherwise, we call the partition wrapper that takes the list and the lower and upper indices and returns a pivot index. If pivot index is the same as k minus 1, we return the element at that pivot index. This is another base case. Otherwise, if pivot index is less than the k minus 1 value, we make a recursive call to quick select on the second half of the sublist, the upper half of the sublist. Otherwise, we make a recursive call to quick select for the first sublist. So let's look at the performance. What is the runtime cost? It depends on where the pivot is located after performing the decomposition. If pivot is in the middle, it's given by this equation. We need to solve a subproblem of approximately half the size of the original problem. The method that performs the partition runs in linear time. This is the best case scenario where we have O of n as the time complexity. Pivot located at an extreme of the list. In this case, the time complexity is given by this equation. You can recognize this as a quadratic function. So the worst case time complexity is O of n squared. Sign up for your free coding interview coaching call. Fuck. Sign up for your free coaching call by going to codinginterview.coach.